Hello everyone, welcome to our beginner series. Today we'll be looking at a very important electronic component, and that is capacitors. In the course of this lecture today, we're going to look at capacitors, color coding, we'll look at the definition of capacitors, how to identify capacitor properties, and the rest. So stay with us. So what's a capacitor? A capacitor is actually a passive electronic component that stores electric charges in an electric field between its metal plates, right? And it is actually made up of two metal plates, which are also known as electrodes, and they are separated by an insulator known as a dielectric. So capacitors mainly are for storing off electrical charges in electric field. All right. So they are mainly in every circuit, capacitors are mostly meant to store electric charges. Okay. And someone may want to ask what's the difference between a capacitor and a battery. All right. Because batteries, rechargeable batteries actually store electric charges too. Okay. So capacitors discharges faster than batteries. Okay, so let's talk about the dielectric. The dielectric material that is used in capacitors could be glass, could be ceramic, could be plastic film, could be paper, could be mica, air, all oxide, any other oxide layer. So bear in mind that the material, the dielectric material used in making a capacitor has a way of affecting the capacitor properties, the capacitor behavior in circuits. All right. So the ability of a capacitor to store electric charges is what is referred to as capacitance. And the unit of measurement is in farad. Take note. All right. So let's look at capacitors, the classification of capacitors. Okay. Capacitors can either be fixed or variable. Okay. So they are either fixed capacitors or variable capacitors. And we have under fixed capacitors, we have polarized and non-polarized capacitors. So there are polarized and non-polarized capacitors. Under variable capacitors, we have tuning capacitors and trimming capacitors. The course of this lecture will focus mainly on fixed capacitors because we'll be making use of them mostly in our practical work as we continue in this lecture. All right. So capacitors can also be classified according to the materials that they are made up of. Remember I said before that the dielectric material that is used in making capacitors has a way of affecting the capacitor properties, all right? So we have ceramic capacitors, we have film and paper capacitors, we have aluminum, tantalum, and other type of capacitors. We have polymer capacitors. We also have super capacitors, okay? And there's, of course, silver, glass, silicon, air gap, and vacuum capacitors, etc. Now, fixed, let's talk about fixed and variable capacitors. The difference, let's know. Fixed capacitors are those capacitors with fixed capacitance value, all right? The capacitance value does not change. You cannot do anything to alter the capacitance value. While variable capacitors are capacitors that have variable or adjustable capacitance value, okay? So non-polarized capacitors and polarized capacitors. Know the difference. Now, after looking at the difference between fixed and variable capacitors, let's look at the difference between polarized capacitors and non-polarized capacitors. Polarized capacitors are capacitors with inherent polarity. And as such, they must be connected in one direction in an electronic circuit. What it means is that they have polarity. There is positive and there is negative. So in connecting them in an electronic circuit, you must pay attention to the positive and the negative terminal, right? So we have non-polarized capacitors. These capacitors do not have any polarity. In other words, you can connect them any way, you can connect the terminals any direction, and it's going to work properly. So you must be very careful when you're connecting polarized capacitors, because if you reverse the polarity, the result would not always be good. Okay. So take note of this. Ceramic and film capacitors are examples of non-polarized capacitors. Okay. Electrolytic and supercapacitors are included in the group of polarized capacitors. Take note. Ceramic and film capacitors are examples of non-polarized capacitors. Electrolytic and supercapacitors are included in the group of polarized capacitors. So let's look at example of polarized capacitor. This is a very good example of polarized capacitor. I'm very sure you must have seen this in electronic circuits several times, different circuit boards before now. Okay, let's look at non-polarized capacitors examples. This is a very good example of a non-polarized capacitor. Okay, another example of a non-polarized capacitor. Okay, now I want you to take note of something here. You observe that this polarized capacitor, when you bring them out, you find out that it has the two terminals. One is actually longer than the other. Okay, so now the shorter terminal, the shorter one is actually the negative terminal of your capacitor. The shorter terminal is actually the negative terminal of your capacitor, while the longer terminal is actually the positive terminal of your capacitor. Then, in any way, probably you did not buy the capacitor from the electronics store. Probably you took it from an old circuit board. You may not actually see the difference between the length of the terminals. So you take note, there is always a shaded part in the capacitor. Is a shaded part. That shaded part, the terminal that is closer to that shaded part, is your negative, and the terminal that is on the unshaded part is your positive terminal. All right, take note of that. Okay, so examples of non-polarized capacitors. Another example, very popular one. Okay, so now let's look at how do we actually interpret the properties of capacitors. How do we identify the properties of capacitors? First, let's start with the electrolytic capacitor, which is an example of the polarized capacitor. First of all, take note, this is the symbol of a polarized capacitor. This is the symbol of a polarized capacitor. And on a polarized capacitor, you see values like this on it. Okay, these values on it, they actually have, there is a code that they are representing. Okay, now when you see something like this, 10 microfarad, okay, 10 microfarad, this 10 microfarad actually symbolizes the capacitance of this capacitor. Okay, and then you have 50 volt here. Now this 50 volt here symbolizes the maximum voltage that this capacitor can handle. All right, so if you exceed the maximum voltage, this capacitor is going to give a negative result. It's going to blow up, it's going to explode. Okay, all right, so if you are using this capacitor in the circuit, make sure that the circuit you are using it, the supply voltage does not actually exceed 50 volt. Okay, let's quickly go back. Let me show you something. So we have this capacitor here now. We have 1000 microfarad. This is the capacitance of this capacitor. Okay, this. Okay, so this we have here is actually the capacitance of the capacitor. Okay, now this one here is the maximum voltage that this capacitor can take. So if you exceed 35 volts for this capacitor is going to blow up. Okay. Now, there are other parameters that we actually pay attention to in capacitors in terms of the temperature and the rest. Here you have 150 degrees centigrade. So at this, anything that exceeds this temperature range, this capacitor is going to get damage. All right. So let's proceed. Okay, let's go back to our table quickly. Now, having known this, all right, having known this capacitor value and the highest voltage for a polarized capacitor, take note of the symbol. I haven't taken note of the symbol. Now, let's look at the non-polarized capacitors. They are actually number coded. They often use numbers to represent their properties. Now, wherever you see this, let's first pay attention to this 104, all right? The 104 here actually symbolizes the capacitance of this capacitor, all right? This 104 here symbolizes the capacitance of this capacitor, okay? Take note. Now, how do you actually interpret the 104? Just like the resistors we talked about earlier, the 104 is also a number code. The first two digits of the capacitor, this first two digits, 1 and 0, becomes the first two digits of your capacitor. Take note, the first two digits there symbolizes the first two digits of your capacitor. And then we have the last digit, this last digit here, the last digit symbolizes your multiplier, all right? And here we have 4, which is approximately 10 raised to power 4, okay? When you multiply that out, you are going to have this figure. So we have 100,000 picofarad, of which when you convert it to microfarad, you are going to have 0.1 microfarad. You get it now? So the first two digits are the first two digits of your capacitor. Take note, the first two digits are the first two digits of your capacitor, and the last or the third digit is our multiplier. So when you multiply that out, it's going to give you this value. Now, most of these capacitors, their capacitance are often smaller than that of the polarized capacitors. They always have small capacitance. Okay. Now, then you look at this, you see other properties too. Okay, you see other properties like this. You see this K here. K there actually symbolizes the tolerance of the capacitor. Just like we looked at tolerance in resistor color coding, we also have tolerance in non-polarized capacitors. Now, you have a figure here. When you see this symbol, it actually represents the maximum voltage that this capacitor can actually handle. Okay, so you have 2E. This 2E, there is the resistor, the capacitor code. All right. So you come here, 2E here under the maximum operating voltage. That's the maximum operating voltage. We have 2E as 250 volts. So you cannot use this capacitor in a circuit where you have more than 250 volts. If you exceed this 250 volts, you're going to damage this capacitor. Please take note of that. Now, so just in case you had 2G, if this place was 2G, for example, it would have been 400 volts. Okay, now remember we talked about percentage tolerance of the capacitor just now. Take note of this. K. All right. K here, you come to the tolerance table, look at K. All right. So what we have here is plus or minus 10% as the tolerance of this capacitor. So with this, we come to the end of this episode. We're going to be creating